there's an underwater wall of oysters that's working to filter and clean the water. These are called vertical oyster gardens.
They dumped 500,000 tons of discarded oyster shells into the Gulf of Mexico. And what happened next defied every scientific prediction on record. Nobody planned for this. Nobody modeled it. Florida's Fish and Wildlife Conservation Commission loaded up barges with scraped-off restaurant leftovers and tipped them into open water, and critics called it exactly what it looked like.
Now, Manatee County has been working with the community to spread these oyster gardens up and down the coastline.
Reckless ocean dumping dressed up as conservation. Fishermen were furious. Environmental groups were loud. Scientists braced for failure, and for the first 18 months, the Gulf floor gave them nothing to argue about. Then the data came back, and Dr. Krimsky, standing over a table of sediment cores, told her team to recheck the numbers, because what those instruments showed shouldn't have been physically possible. What formed down there is still expanding today. What they dumped, and why nobody expected this. Between 2007 and 2024, the Florida Fish and Wildlife Conservation Commission ran one of the most controversial coastal experiments in state history. The premise was almost absurdly simple. Collect discarded oyster shells from restaurants and seafood processing plants all across Florida, truck them to the coast, load them onto barges, and dump them into the Gulf of Mexico near Cedar Key.
As Fox 13's Kimberly Cuisin shows us, they start with leftover oyster shells from local restaurants.
Over 500,000 tons of them. Not precision-engineered reef modules, not strategically designed marine structures, just leftovers. Shells scraped off plates, shoveled out of processing facilities, loaded onto barges and tipped into open water. The opposition was immediate and fierce. Environmental groups called it ocean dumping disguised as conservation. They warned the shells would smother whatever fragile life remained on the soft, sandy bottom. Local fishermen who had spent generations working those waters feared sediment burial, disrupted currents, and permanent destruction of fishing grounds their families had relied on for a century. Marine biologists pointed to previous failed attempts at artificial reef construction and argued that dumping calcium debris onto an already stressed ecosystem would accelerate its collapse, not reverse it. The criticism wasn't fringe. It was loud, credible, and backed by real ecological concern. And yet, the commission pressed on. Their logic was stark. These shells were going to landfills anyway. If there was even a chance they could function as reef substrate, the experiment was worth running. The program had no guarantee of success. It had no model to follow. It had only the uncomfortable awareness that doing nothing had already failed.
Putting vertical oyster gardens out in the environment promotes oyster growth underneath docks, and scientists now know that oysters are capable of filtering water and removing nutrient pollution from our waterways.
And that Florida's coastal ecosystems were continuing to deteriorate while conventional approaches produced marginal results at enormous cost. The Commission's internal projections gave the program a 30% chance of producing any measurable biological response within 5 years. That was considered optimistic. Here's the catch. Nobody, including the scientists who designed the program, actually expected it to work this fast. When those first monitoring teams returned 18 months in, they were braced for the worst. What Dr. Krimsky found instead, clusters of marine organisms colonizing the shell mounds at rates with no precedent in the scientific literature, stopped the debrief cold. The shells weren't acting as passive debris. They were functioning as biological triggers, and nobody could fully explain why. To understand what was happening, you had to look at something so small it was effectively invisible. What was unfolding down there was stranger than anyone had imagined. The invisible phase. The pioneers weren't fish. They weren't oysters. They were bacteria. Within days of the shells hitting the seafloor, microscopic bacteria began colonizing the calcium carbonate surfaces, forming thin biofilms, structured living carpets that transformed dead shell into functional microhabitat. These weren't random bacterial patches. They were organized biological infrastructure laying the groundwork for everything that would follow. And get this, the shells were doing their own chemistry. Oyster shells are composed primarily of aragonite, a form of calcium carbonate that dissolves slowly in seawater. As those shells released calcium ions, they created tiny alkaline microzones in the surrounding water. Those localized chemical shifts were exactly what calcifying organisms, barnacles, tube worms, juvenile oysters, needed to attach and grow. The shells weren't just providing physical surface. They were manufacturing the conditions for their own colonization. Weeks later, diatoms and microalgae moved into the biofilms, creating the base of a rudimentary food web. Microscopic crustaceans and larval mollusks followed. Those grazers drew the first juvenile fish. Each stage fed the next, a self-reinforcing loop building itself invisibly out of discarded seafood scraps. Here's what that means. Sandy seabeds cannot do this. Sand offers no attachment surface, no chemical microzones, no structural complexity. The soft-bottom Gulf floor was biologically trapped. The shells bypassed that trap entirely. By the end of the first 6 months, Dr. Krimsky's sediment cores showed shell surfaces coated in layered biofilm and microalgae.
Oyster shells are picked up from a number of restaurants and then they're brought here, where they sit in the sun for about 3 to 4 months.
To a camera above the waterline, the site still looked like failure, but the data told a different story. In less time than a traditional artificial reef shows any biological response at all, the shell deposits had established a complete microscopic ecosystem. Most reef restoration projects never clear this hurdle. They provide structure, but fail to trigger the chemical cascades that convert dead material into living habitat. The discarded oyster shells were doing both simultaneously, faster than anything on record. And the sites were only going to get stranger from here. The invisible scaffolding was in place. What happens when the oysters actually arrive is one of the fastest biological turnarounds ever documented. Subscribe so you don't miss what came next, because the numbers Dr. Pine was about to record had his team rechecking their methodology entirely. The return of the reef builders. Oysters need hard surfaces to survive. That single constraint had been quietly strangling Florida's Gulf Coast for decades. Oyster larvae, called spat, drift in the current, searching for substrate. In a healthy reef system, that substrate is the accumulated shells of previous generations, centuries of dead oyster layered into a hard, complex platform, filtering water, preventing erosion, and providing a home for an estimated 300 different species. Remove that substrate, and you don't just lose oysters. You lose every species that depends on the structural complexity oysters create. The entire architecture collapses into open sand. Florida's natural reefs had been gutted. Overharvesting, pollution, and coastal development had dismantled a network that once spanned hundreds of square miles. By the early 2000s, larvae were drifting through open water with almost nowhere to land. No substrate, no settlement, no new oysters. The cycle was broken, and the Gulf had no mechanism to fix it alone. What had taken centuries to build had been dismantled in a matter of decades, and unlike a forest that can reseed itself from the edges, a reef without substrate leaves nothing for the next generation to land on. The collapse was self-reinforcing in the worst possible direction. Here's the deal. The dumped shells solved this bottleneck almost immediately. Each pile was a concentrated landing zone, positioned exactly where Gulf currents would carry drifting spat. Within the first year, University of Florida Marine Lab researcher Dr. Bill Pine, standing over a sampling grid at one of the Cedar Key sites, watching the data come in, documented juvenile oysters attaching to the deposited shells in numbers that far exceeded every projection. The larvae were finding surface, settling, growing. By year 2, those juveniles were reproductive adults producing larvae of their own.
The amazing thing about oysters is that they filter 50 gallons of water per oyster per day,
which settled on the existing reef and added a second generation to the structure. Human hands had created the initial conditions. Nature had taken over completely. By year 3, monitoring surveys recorded an average of 847 oysters per cubic meter of deposited shells. Nearby, soft-bottom areas with no substrate supported virtually none. The reef was no longer confined to the original deposition footprint either. Oysters were dying, contributing shell, and providing substrate for the next wave. Vertical growth, horizontal expansion. The reef was building itself. And then came the moment that changed the entire conversation. Charter Captain Mike Lenz had been one of the loudest voices against the shell deposition program from the beginning. He had testified against it, warned it would ruin the fishing grounds his family had worked for. 3 generations. In 2013, standing at the rail of his boat over one of the established reef sites, Lenz watched a thick school of redfish holding in the current around a shell mound and said something he had never planned to say. "I was wrong. I've never seen fish stack up like that in 25 years on this water." That reversal wasn't just one man changing his mind. It was the moment lived experience caught up with the data. But the fish were only the beginning of what these reefs were about to do. When the fish arrived, everything changed. Reef fish don't wait for an invitation. The moment structural complexity appears on a featureless seafloor, they find it. Within 2 years of the reefs establishing themselves, Dr. Pine's fish surveys near Cedar Key came back with numbers that sent the team back to recheck their methodology. Biomass around the reef sites had increased by more than 340% compared to control areas. Species diversity was up 280%. These weren't fish aggregating from somewhere else. They were juveniles surviving in habitat that hadn't previously supported them. The reef was producing life, not concentrating it, producing it. Redfish arrived first, tucking into the complex shell structure to feed and hide from predators. Sheepshead followed, thriving on the invertebrate communities coating the hard surfaces. Flounder worked the edges. Snook appeared in numbers not seen in those waters in years. And get this, Mike Lenz wasn't the only captain who reversed his opposition. Charter operators across Cedar Key began formally requesting new reef sites from the same commission they had fought against 6 years earlier. A 2016 economic analysis found that every dollar invested in the reef program generated an estimated $11 in measurable economic activity. Fishing licenses, charter fees, fuel, lodging, restaurant revenue. For small waterfront towns like Cedar Key, that wasn't an abstract statistic. It was the difference between staying open and closing down.
You can see today, even over the reef where there is water, how clear the water is, and that's because those filtration processes are already occurring.
The ecological cascade continued upward. Octopuses established territories in the reef's complex gaps. Sea turtles reappeared. Dolphins were observed hunting systematically at the reef edges, working the dense fish concentrations. Hotels, bait shops, and waterfront restaurants all reported measurable revenue increases tied directly to the marine surge around the reef sites. Every new arrival reinforced the food web beneath it. The system was growing more complex, more stable, and more resilient with each passing season. Here's what the data confirmed that made this significant beyond the visuals. Artificial reefs made of concrete or sunken ships are notorious for concentrating fish that already exist nearby. Redistributing a fixed population around a new landmark. That can look dramatic in a survey without representing any actual increase in marine life. The Cedar Key reefs were different. Juvenile fish counts, animals born in those. High waters, surviving to maturity there, were the primary driver of the increase. New life, not relocated life, but something else was happening to the water itself. Something nobody had predicted, and its consequences reached far beyond the reef. The billion-gallon cleaning machines. One adult oyster filters between 30 and 50 gallons of seawater every single day. Run that number across hundreds of thousands of oysters thriving on the restored reefs. Entire reef systems were now processing billions of gallons of Gulf water daily, extracting suspended particles, excess nutrients, harmful bacteria, and agricultural runoff. No machinery, no electricity, no maintenance cost. Nature had built an industrial-scale water treatment plant out of discarded restaurant waste. And get this, the Gulf Coast has a chronic runoff problem. Nitrogen and phosphorus from farms and urban development pour into coastal waters constantly, fueling harmful algal blooms that cloud the water, suffocate marine life, and periodically trigger mass fish kills. The oyster reefs were attacking that problem at the source. Water clarity around the reef sites began improving measurably within a few years. Dissolved oxygen levels rose, nutrient concentrations dropped, and the improvements weren't staying local. They were radiating outward in a growing radius around each site. Clearer water let sunlight penetrate deeper. Seagrass beds began expanding into zones that had been too murky for years. Seagrass then stabilized sediment, which reduced turbidity further, which let more light through, which enabled more seagrass growth. A second self-reinforcing feedback loop triggered entirely by the first. This was the part that surprised even the researchers who had expected the filtration to work. They hadn't predicted the cascade would reach this far. Researchers estimated the filtration services alone were worth tens of millions of dollars, value that would have required extraordinary mechanical infrastructure to replicate. Here's what that means for the bigger picture. Alabama launched its own shell recycling program by 2015. Mississippi followed. Louisiana initiated massive reef building initiatives. The Billion Oyster Project in New York Harbor adopted the same principle in one of the most polluted urban waterways in North America. Coastal engineers in Canada, Australia, and Europe began studying the Florida model. The concept had a name: circular environmental design. Waste materials repurposed as functional ecological infrastructure, not as a stopgap, but as a genuine design strategy. But none of that fully answered the question nobody had thought to ask yet. Could these reefs survive what the Gulf throws at them every few years? The answer was about to arrive without warning. The hurricane test. Nobody planned. September 2017. Hurricane Irma, Category 4. Wind speeds exceeding 150 miles per hour, catastrophic storm surge, waves hitting the Gulf Coast with enough force to strip beaches and reshape shorelines overnight. Coastal communities near Cedar Key braced for the kind of destruction these storms reliably deliver. In the aftermath, the conversation was expected to be about losses, damaged docks, eroded banks, ruined fishing grounds. It wasn't. When damage assessors moved through the area after Irma passed, they found something that stopped the conversation cold. Shorelines backed by the restored oyster reefs had experienced dramatically less erosion than unprotected stretches nearby. On average, erosion was reduced by 30 to 40% compared to adjacent soft sand beaches. The reefs had acted as natural wave attenuators, layers of living oysters stacked on layers of shell, rough and irregular, absorbing and dissipating wave energy before it reached the shore at full force. No smooth surface for waves to run along, just friction, breaking momentum, reducing height, protecting the land behind it. The math was almost impossible. Engineers estimated the reefs had prevented approximately $3 million in coastal property damage during Irma alone. The total cost of the entire 15-year restoration program was approximately $5 million. The reefs had nearly paid for themselves in a single storm. But here's something seawalls simply cannot do. Seawalls crack, riprap shifts, steel corrodes, concrete eventually fails. The oyster reefs, by contrast, are self-repairing. Storm damage triggers new larval settlement. Each subsequent generation adds height and structural complexity. The barrier was growing stronger after every storm, not weaker. Here's the deal. For decades, the default response to shoreline erosion had been hard engineering. Seawalls, riprap, concrete barriers. Expensive to install, requiring ongoing maintenance, and frequently failing under extreme conditions precisely when they were needed most. The oyster reef results introduced a competing logic. Let biology do the structural work. Let organisms that have been engineering coastal environments for millions of years do what they evolved to do. Traditional shoreline armoring typically runs hundreds of thousands to millions of dollars per mile. The Cedar Key program achieved comparable or superior erosion protection at a fraction of that cost, and the protection improved every year without additional investment. For coastal policymakers who had been wrestling with accelerating erosion and increasingly severe storm seasons, the question was no longer whether this approach worked. The question was how fast they could scale it. Coastal engineers who had dismissed oyster restoration as fringe conservation suddenly had a problem. They had no convincing argument against it. The program they had ignored for 15 years had just outperformed every hard engineering solution they had ever funded. But the most extraordinary part of this story was still unfolding. The living structures that refused to stay still. By the early 2020s, the Florida reefs had done something no artificial reef in the region had managed. They had grown beyond their original footprint, substantially, measurably. The oldest sites had roughly doubled in total area since initial deposition, expanding outward in every direction without any additional human input. The mechanism was the oyster reproductive cycle itself. Each generation settled on existing structure, matured, died, and contributed shell for the next wave of larvae. Vertical accumulation, horizontal spread, no assistance required. Early deposits were irregular mounds of loose calcium. The living reefs that emerged were architecturally elaborate, vertical profiles, gaps between dense oyster clusters, overhangs, interlocking surfaces creating dozens of distinct microhabitats. Not a substrate, an ecosystem. And get this, researchers were now finding evidence that dense oyster reefs sequester organic carbon in their shells and surrounding sediments, trapping greenhouse gases that would otherwise contribute to ocean acidification and atmospheric warming. Oyster restoration had begun appearing in climate adaptation strategies, not just habitat recovery and coastal defense. Carbon management. The ecological case had expanded into a climate case almost by accident. Biodiversity metrics at the mature sites were approaching levels recorded at pristine natural limestone reefs. Endangered sea turtles returned. Dolphins hunted the reef edges systematically. The Gulf was rebuilding itself around the oysters. Here's what nobody expected when this all started. The reefs weren't aggregating existing marine life. They were generating new life, continuously season after season, without help. The shell deposits of 2007 had seeded a cycle now perpetuating itself indefinitely. Each oyster that lived and died contributed substrate for the next generation. Each generation expanded the reef's footprint. Each expansion created new habitat, filtered more water, protected more shoreline, and supported more species. The restorationists who had designed the program had hoped to start something. They hadn't fully reckoned with the possibility that what they started might never stop. The intervention had ended. The ecosystem had not. It was running on its own, biological momentum. The data suggested it would continue for decades, potentially centuries to come. That outcome had been unimaginable in 2007. It was measurable fact by the early 2020s. The entire scientific and engineering establishment that had doubted the program was now studying it as a template. International interest followed. Researchers in Canada, Australia, and Southeast Asia were all asking the same question their American counterparts had taken 15 years to answer. Conservation engineers, who had spent careers designing concrete and steel barriers, were quietly requesting site visits to Cedar Key. The question was no longer whether oyster shell reefs worked. The question was why it had taken so long to try. 500,000 tons of oyster shells, discarded, written off, tipped into the Gulf without any certainty that a single useful thing would result. And look what formed. If you want to see where oyster restoration goes next, the science is even more extraordinary than what you've just seen. Hit subscribe and check out the next video on your screen.